Hey everyone, welcome to the September webinar presentation by the Underground Construction Association Young Members Group. My name is Shannon Goff. I'm one of 3 members of UCA of SME Standing Committee for the UCA-YM. I am the University Outreach Chair, and I'm joined by Anthony Bauer, the Chair, and Aaron Clark, the Professional Development Chair. As always, please join us for our webinar series on the last Wednesday of each month. The presentation in October will be on October 28th. Our presenter is still being organized, so keep a lookout for an email with the details for that webinar. You can sign up for our email list as well as register for next month's presentation on our website. Today we continue the webinar series with a presentation by Nasri Munfah, Senior Vice President at HNTB, and Vojtech Gall, Principal at Gall Zeidler Consultants, on the Eurasia Tunnel as part of the Istanbul Strait Road tube crossing in Istanbul, Turkey. The project is in the advanced stages of construction with an anticipated TBM breakthrough this month. Nasri Munfah has more than 30 years experience of project management in tunnels and underground engineering projects. He has been responsible for managing all phases of tunneling projects from feasibility and conceptual engineering through final design and construction. He was a principal investigator and co-author of FHWA's Technical Manual for the Design and Construction of Road Tunnels. In addition, he is presently an adjunct professor at Columbia University. He has published and presented over 50 technical papers, has received many awards, and is an active member of various national and international tunneling and underground societies. Dr. Gall has over 25 years of experience in the design, construction, and construction management of tunnels and underground structures. His expertise spans from soft ground and rock TBM tunnels, tunneling, and cut and cover techniques. He frequently serves on expert review panels dedicated to the investigation and improvement of tunneling schemes from initial inception stages through final design development. His peer review services encompass a wide variety of facilities ranging from hydropower schemes in remote settings to complex transit structures in urban settings. He has authored over 40 technical publications on the subject of tunneling and lectured extensively on the implementation of modern tunneling techniques. With that, I'm going to turn control over to our speakers, Nasri and Vojtech. Thank you very much for presenting to us today. And when you're ready, you can share your screen and begin your presentation.
Thank you, Shannon. This is Nasri Munfah, and Vojtech is with me here in my office, and we'll be making the presentation together. Just a minor editorial. Shannon mentioned that the TBM was supposed to break through in September. Just to let you know that it beats its schedule, and the breakthrough took place in August, on August 22nd. The Istanbul Strait project is one of the iconic projects around the world right now. In today's topic, we're going to be covering an overview, technical challenges, the TBM Bored Tunnel, the NATM Tunnel, and to show you the construction progress up to now. The project consists of 3 major areas, 3 major components of the project. It is a road tunnel connecting the Asian side of Istanbul with the western side of Istanbul, which is the European side. It is one of 3 major programs that are going on in Istanbul at the present time. One is the third Bosphorus bridge that is taking place at this location, a new international airport somewhere in this vicinity, and our project, which is the Eurasia Tunnel. The Eurasia Tunnel will consist of 3 parts: European side, the Asian side, and the tunnel itself, as we'll be talking about in a minute. Okay? This particular project is the first public-private partnership project in Turkey. It is being delivered in a BOT basis, which is build, operate, transfer. The concessionaire for the project is a joint venture of Yapı Merkezi, which is one of the largest Turkish contractor, and SK Engineers and Construction, which is a Korean contractor. jointly they form a joint venture called Atash. Atash, as the developer, is contracted to a construction joint venture, Yapi Merkezi SKJV. The project total investment will be about $1.3 billion, in which $960 million were from various financial institution loans, and the developer put $320 million. To recover the cost, the project will be operating for 26 years, and there is a guaranteed of traffic volume of 80,000 vehicles per day. However, based on traffic studies, it was determined that the traffic could be as much as 100,000 vehicles a day. It will provide a direct and short connection between the Asian and the European parts of Istanbul, and it is made specifically for cars and minivans only. So with this project, at the present time, the traffic going between the Asian side and the European side, it goes around one of the two existing bridges, which is the shortest distance, will be about 100 minutes of travel time. With the completion of the tunnel project that we're talking about today, the traffic will be about 15 minutes to get to the same point. So it will provide a shortcut between the Asian side and the European side. It will provide considerable relief of traffic congestion on the Bosphorus bridges and significant time saving and associated environmental improvement in terms of emission and pollution. In addition to that, there are two major airports in Istanbul. One is the Atatürk International Airport, and the other one is Sabiha Airport. The Sabiha Airport is the local the local airport within Turkey, and this will provide again a short connection. One of the unique things about it, because the project is in the historical part of Istanbul, having a tunnel rather than a bridge, it will improve the visual appearance and will not impact the silhouette of Istanbul. The project is being delivered by a global team. Beside the developer and the contractor, the design leader is Parcel Brinkerhoff. HNTB with Gall Zeidler is the design verification engineer. The due diligence was done by Arab from the UK and so on. Geotechnical studies were done by Fugro. Tunnel operation will be done by Aegis from France, and the TBM supplier is HellenConnect from Germany. As you can see, it is a global team to bring the best available resources and technologies to the project. I'm going to go over the project overview right now. This is on the west side. This area is the historical part of Istanbul, and this is in the European side. Of course, there is the Bosphorus crossing here, connecting the Black Sea to the north with the Marmara Sea to the south. On this side is the Asian side, and this is mostly residential. So in a sense, there is a lot of traffic going between the Asian side and the European side. The project consists of three parts, as I said earlier. The first part is in the European side along Kennedy Boulevard, which consists of about 5.4 kilometers of, in a sense, road widening, bridges, underpasses, and pedestrian crossings. Then the tunnel itself, which is part two, as well as the Asian side. The Asian side consists of 3.8 kilometers of road widening also, and modification to the connections to the local streets and to the existing freeway system. The tunnel itself, which is part two, it consists of 5.4 kilometers of 2x2 traffic lanes on top of each other, as you can see in the cross section. It consists of a TBM tunnel, which is about 3.3 kilometer, and two NATM tunnels on the eastern side, on the Asian side, of 930 meter each. In addition to that, there are the cut and cover as well as the U sections and all the associated facilities to go with that, including the toll plaza, ventilation, fire life safety, and operation and maintenance buildings. The bored tunnel itself is in order to accommodate the two traffic envelopes toward the eastbound toward Asia and westbound toward Europe. The tunnel cross-section was determined to require 12 meter of inside diameter, plus precast segmental liner of 600 millimeter thickness would result in a 13.2 meter in diameter, outside diameter. The upper roadway deck was designed to be cast in place, while the lower roadway deck was designed to be a precast. In addition to the upper roadway and the lower roadway, there is the utility gallery that providing all the electrical and mechanical systems. The upper deck and the lower deck are interconnected at various intervals to provide for emergency evacuation, as well as at certain intervals there is emergency stop for breakdown of if car broke down. The ventilation is provided by jet fans plus exhaust fans at the two ventilation building, one on each end, in addition to all the traffic signal and signs and the fire life safety requirement within the tunnel itself. As I mentioned, the upper and the lower roadways are interconnected with emergency passageway. Just in case of fire in one of the two roadways, then the people can evacuate to the upper roadway, and that become the emergency escape route. As for breakdown, at every 600 meter, an alcove was provided for car breakdown or replacement of tire or things of that nature in order to maintain the traffic going through. The project faced many challenges and many risk issues, and we're going to be discussing some of them today, obviously not all of them because of the limited time that we have. Some of the challenges is the large diameter, the fact that a double deck large diameter in that location. Another major challenge is the complex and variable geology and hydrology in the area. In these conditions, we are encountering mixed phase conditions that need to be addressed during the design as well as during construction. In addition to that, the tunnel is very deep in order to cross the channel that happened to be 62 meter deep. As a result, the tunnel is it's about 106 meter deep, which would result in 11 bar of water pressure. Furthermore, there is high seismic zone that we have, that the tunnel has to be designed to accommodate high seismic conditions, as well as complex transition structures on both sides of the tunnel, because we are going from 2 over 2 to 2 next to each other, and those transition zones are deep cut and cover structures adjacent to the water body. As part of risk mitigations, the owner as well as the developer identified a need for independent design verification. That's where Gall, Zeidler, and HNTB teamed together to provide this service to the client. The independent design verification role is critical in terms of addressing all critical issues in terms of reviewing the design for correctness, identifying potential risk issues, identifying potential corrective action, as well as providing betterments and potential solutions to challenges of the project. So this system of independent design verification to control risk was implemented throughout the entire phase of the project, from conceptual planning, final design, construction, as well as facility operation. And it was not just limited to the structural component, but also expanded to all issues, including mechanical, electrical, fire life safety, all related elements that required for the functioning of the facility. A detailed design verification process was established and was reviewed by and approved by the ATASH, the developer, as well as by the owner, in which every element has to be going through a detailed independent review and verification. All calculations has to have independent check. All analysis will have to be independently reviewed and verified. I'd like to talk a little bit about the geology of the area. The strait, the Bosphorus Strait, was formed by major historic tectonic forces that resulted in the two rock formations which are on both sides of the Bosphorus, which is called the Trachea Formation, highly fractured and faulted and intruded. The Trachea Formation consists mainly of sandstone and mudstone, and however, it is, as I said, highly fractured and water-bearing strata. In addition to that, it has several locations a lot of volcanic dikes intrusion. Going from the Trachea Formation into alluvial deposit within the body of the water. The alluvial deposit consists of coarse-grained soils, including gravel, sand, as well as fine-grained soils, silts and clay, and which varies vertically and longitudinally. Extensive geotechnical investigation was performed on land as well as in the water. Fugro did a lot of this investigation, as you can see the borings, the marine borings that were taken along the alignment of the project. So with that condition, with the rock formation and the intrusion of the rock, plus the alignment going from the rock into the soft ground, then from the soft ground into the rock again, we end up having various mixed phase conditions. Rock to soft ground to rock, as well as within the rock strata itself between the Trachea Formation and the volcanic dikes. As I said, the Trachea Formation consists of sandstone, siltstone, and mudstone, highly fractured. And the volcanic dikes, as you can see in this illustration here, you can see that the volcanic dike is almost half the cross-section. So we are within the same cross-section, we are hitting very hard material as well as very soft material, highly fractured. In addition to that, there are faults at various locations along the alignments, and the rock property varies within the cross-section itself as well as varies along the alignment and so on. The other challenge is the seismic condition of the area. The location happened to be at a cross between three continents. So there are three tectonic plates, the African, the Anatolian, and the Eurasian plates. They all happen to be at that location. As a result, a complex fault system was developed in that area. Again, this is the location of Istanbul here. This is the Marmara Sea, this is the Black Sea, the Bosphorus is this connection there, and the movement of the three tectonic plates resulting in a significant formation of fault system in the Sea of Marmara. The biggest one is it's called the Marmara Fault System, which happened to be the closest to the alignment of the tunnel, which is about 16 kilometers. That increased the probability of a strong earthquake happening in the area. We anticipate that at least one medium intensity earthquake will happen in Istanbul every 50 years. Okay? Therefore, the tunnel has to perform under earthquake conditions, and in a couple of situations. One is operational, continue to be operational, and the other one is repairable very quickly. In order to build this tunnel, the design called for a TBM. The selection was made using Herring-Connect Mixed-Shield TBM, which is a slurry TBM in a sense. The TBM was manufactured in Germany and was delivered to the project site. The outer diameter of the TBM is 13.71 meter with a length of 120 meter, and it's capable of handling 13 bar water pressure. The TBM design was designed to handle mixed phase condition and to operate mostly always in a closed mode situation. As you can see here in the face of the TBM, it had disc cutters as well as soil knives or soil scrapers, and they are distributed throughout the face, and they are made into available to be able to be accessible from the back. I will talk about that a little later. In addition to that, there is behind here, there is a jawbreaker to be able to deal with boulders as well as cobbles that may be encountered. The plan was to advance about between 6 to 7 meters per day, average daily advancement, and the maximum they were able to achieve was 18 meters per day. That was within the planned schedule and was achieved. It was launched on April 19, 2014 and completed its drive on August 27, 2015. Here are some pictures of the assembly of the TBM within the launch shaft, which will act also as the transition, the Asian transition box. As you can see from this picture, the Asian transition box is very deep. It is obviously close to the water, and it is very challenging to build. It was in the range of about 120 meters in length with variable widths and variable depths. As I said, April 19 was the start of the TBM. That was the launch day. And it progressed very successfully. The TBM liner consisted of 8 segments plus a key. The segments are 2 meters in length and 600 millimeters in thickness. They are double reinforced, and it was because of the high water pressure, it was provided with double gasket. The segments were bolted in both directions with shear keys and sliding rods. Here are pictures of the segment manufacturing. As you can see on the lower left side, you will see the reinforcing cages plus the dismantling of the segments, as well as you can see the shear key of the segments. The segments were cured and then delivered to the site, and each stack consists of 8 segments, and the key were identified, and each one of them has a barcode that will identify every segment and every ring and all the properties that were there. The segments were delivered unusually to the tunnel using rubber tire trucks, as you can see in the lower right-hand side picture. As I mentioned, there are some challenges and how the project dealt with them, including high water pressure as well as the seismic conditions. I will talk about some of those and how were dealt with. Under high water pressure, it's difficulty for TBM maintenance and replacement tools as well as potential water leakage. Therefore, the design called for cutter change system to be done under atmospheric conditions, as well as identification of wear detection in the cutting tools, as well as providing ability to have hyperbaric intervention if needed. In terms of water leakage, double gaskets were provided, as I mentioned. As for the seismic conditions, different ground response during the earthquake to a different characteristic of the ground conditions had to be assessed. Therefore, we considered 8 sets of analysis, and the project identified the needs of seismic joint to be placed. And in a sense, 2 seismic joints were provided at the interface between the rock and the alluvial material. Regarding the high water pressure, as I mentioned, the cutter changes can be done under atmospheric condition from the back side. As you can see here on the left side picture, an illustration showing the ability to pull the cutter ring assembly out and replace it with new cutters. So there were 35 pieces that can be replaced from the back. In addition to that, the cutting knives were, most of them were able to be replaced from the back. The picture in the middle, you would see the condition under which one of the workers was replacing one of the disc cutters from the back. However, certain components of the TBM cannot be replaced from the back, and therefore there is a need to have hyperbaric intervention if needed. To do that, under 11 bar of water pressure, there was a need to do a saturation diving. The saturation diving was divided by a capsule that can be brought to the site, brought into the face of the TBM, and under pressure, saturation diving can be done to do any maintenance or repair on the front of the TBM. The saturation diving would require significant amount of time for the workers to be under high pressure, high air pressure, and as a result they have to be in a capsule for several days or even up to a week or more to be able to adjust in terms of the temperature, in terms of the pressure. The Tailskin seal system was also provided in order to provide the grout immediately as the TBM advanced and the ring is pulling out into the ground. The grout was done through the shield itself, and 3 brush packing were provided in addition to an inflatable skin tail seal that can be done to in case of an emergency, in case of a need to do a repair. The system consists of 3 brush seals plus, as I said, the inflatable seal. And here's an illustration of the brushes as well as pictures of the brushes, the tail brush packing in the factory. The TBM, the liner, the segmental liner were double gasketed for the high water pressure, as well as there was a need to have bolted in both directions, obviously for connectivity as well as for seismic, for resisting of the seismic loading, as spear bolts were used to make the connections. Regarding the seismic condition, as I said, two levels of design earthquake were considered. One is the functional evaluation earthquake, which has high probability of occurrence, 20% in 100 years. That consists of an earthquake magnitude of 7.5 on the Marmara Fault. In this condition, life safety must be maintained and to continue operation of the facility with slight to no damage to the structure. Upon inspection, be able to put the tunnel back in operation. As for the safety, the other level is a safety evaluation earthquake, which has a smaller probability, which is 4% in 100 years, or a return of 2,500 years. That is a magnitude of an earthquake magnitude of 7.5 anywhere. In that case, life safety has to be assured and no failure or flooding of the tunnel. Minor structural damage to be repairable within a reasonable time. The analysis that was done, extensive analysis was done taking into consideration the various ground conditions. This is one example of the analysis that shows the forces, and in this case I believe the normal forces, to show that there is an excessive of forces at the interface between the rock and the soft ground. By introducing seismic joints, the lower portion of the graph, it shows that the loads or the forces dropped dramatically. So two seismic joints were introduced at the interface between the rock and the soft ground, and the seismic joint consists of two steel joints in a sense and interconnected with omega seals as well as pistons that would allow the movement in the expansion and contraction of 75 millimeters in each direction, as well as shear deformation 50 millimeter. Here are pictures of the installation of the seismic joints and on the left side, and then the installation of the omega seal on the right hand side of the joint. The joint can move, as I said, horizontally in all three directions, compression, expansion, as well as shear deformation. And here is the seismic joint completed after installation. At this point, I would like to turn it over to Vojtech to talk about the NATM segment.
Thank you, Nasri. Thank you, Shannon, for the kind introduction. I would like to spend a few words on describing the NATM tunneling on the project. You see here up in the upper half of the page the two distinct NATM tunnels. On the Asian side, so to the left would be towards the European side, to the right, to the east, into the Asian side. The tunnel cross-section that was selected is a classical dual lining NATM section with an initial shotcrete lining and a final cast-in-place concrete lining with a PVC membrane for waterproofing sandwiched in between, and the cross-section is shown here in the lower left corner. The invert is rounded basically because of two reasons. One, the trachea formation, which was the main host formation for the tunnels, is a relatively soft, weak, fractured rock mass, and the hydrostatic pressure is relatively high, with the groundwater elevation being just a few feet underneath the surface. On the right side, you see the portal. That would be the portal here on the left side, is shown here, essentially again looking back towards the Asian side. And you see the tunnels being configured with a relatively narrow pillar. And the reason is that the turnover of the 2 lanes from the upper deck and 2 lanes in the lower deck happens mainly in the cut and cover section, but transitions also into the 2 NATM tunnels until finally on the Asian side, when the portal exits the lanes out of the tunnel, they become basically side by side. So it's a classical application of the NATM at a length of some 900 plus meters. The use of a TBM, of a new TBM, a smaller TBM, would not have been justified. And also based on case histories in Istanbul, NATM has shown to be a very successful tunneling technique in the trachea formation. So as Nasri mentioned earlier, we were involved as the independent design verifier, and were looking at the design prepared by Parsons Brinkhoff, supported by a local tunneling consultants, IGT, from Austria. And with that, we looked at the design methodology, in particular the sequence and support of excavation for the tunnels. We looked at tunnel specifications and quality of materials. And in order to support our findings, we developed a series of a total of 9 finite element models at typical and critical locations along the alignment to look into the adequacy of the temporary and permanent tunnel linings. So these are typical tasks that one carries out as an independent design reviewer. Here you see in this slide a summary of the alignment, the cross-section showing initial support with shotcrete lining and a systematic rock bolting on the right upper side. And what is also noteworthy is that we had to look at 4 cross passages for NFPA or life safety requirements, 1 lay-by section, and 4 mechanical electrical plumbing rooms that housed installations to support the tunnel operations when completed. The tunnel excavation was typically done in a top-heading bench and invert excavation. As you see here, this would be the top-heading, bench, and invert. On the right side, we see or look at a typical configuration of our finite element models for the design verifications. And from looking at not only the structural calculations but also design drawings, specifications, and drawing from experience on large international projects, we came up with a summary of NATM recommendations that I will lay out in a few minutes. This again a summary of the trachea formation, which is essentially a interlayered system of shales, siltstones, and mudstones, highly fractured, also faulted and folded, weathered with intrusions of diabase, as mentioned earlier. And what comes on top of it is a challenge, for example, here at the east portal, of relatively shallow tunneling and tunneling underneath a highway bridge and its foundations. And so a big concern was to control the settlements, and for that the designer foresaw and rightfully implemented the use of a pipe arch canopy as a positive pre-support in the tunnel roof. Here again, this typically layered system of the rock strata between the mudstone, sandstones, and the individual layers are essentially very similar by composition, but are of varying strength and deformation characteristics. Another model developed here, in particular for the low overburden at its lowest region, which was on the order of some 8 meters. The recommendations included looking at the trachea formation, and in particular during tunneling, in order to better control the groundwater around the tunnel. to develop a systematic dewatering system. Further, we called for the installation of additional instruments to be able to perform a more rigorous monitoring, instrumentation and monitoring at complex. Complex means in this case typically overburden structure areas. And we also called for the development of a systematic toolbox to implement contingencies should the ground conditions be of lesser quality than anticipated, to be able to install more shotcrete, additional rock bolts, additional pre-support, and also potentially subdivide the face to be able to control the face conditions better. We also engaged the contractor during design development in a discussion to use fiber reinforced shotcrete instead of welded wire fabric. However, found out then later on during construction that the welded wire fabric, because it's well known in Turkey and Istanbul, was the preferred method by the tunneling subcontractor. So the tunnels were supported by welded wire fabric reinforced shotcrete. A few photographs showing the portal side, and here you see the penetration into the support of excavation secant piles, removal of these beams which were held by tiebacks, and later on this side a excavation of the left side wall drift into the tunnel. Here you see again the narrow pillar with the two tunnels side by side but of different elevation, and here a typical top heading excavation with the bench being brought to the top heading face within about 2 tunnel diameters. Here you see on the left side a typical NATM installation of initial shotcrete lining, a sawtooth excavation as we call it, to be able to install pipe arch pre-support from within the tunnel. Here excavation into one of the 4 cross passages. Here you see the waterproofing in the invert section with a protective concrete layer and a scaffolding to be continuing waterproofing installation. And here again the typical tunnel lined with initial shotcrete lining and waterproofing in the invert, which will be continued all the way around the entire perimeter. And with that, I would like to give it back to Nasri. Thank you. And Nasri?
Thank you, Vojtech. I'll just show you some of the location of the retrieval shaft, or which is in the European transition box. Again, the European transition box is a variable width box that will act as a transition from 2/2 to two lanes adjacent to each other. It was constructed using diaphragm walls, or slurry walls as we refer to them here in the U.S., and with concrete whalers and cross bracing, as you can see here. While the TBM is advancing, the corbel construction and the upper slab construction was proceeding behind it using, as you can see here, special scaffolding equipment, and the concrete slab had to be concreted in order to be able to meet the schedule. On the left picture, it shows the rebars for the upper roadway slab, and on the lower right hand it shows the corbel for that slab. As I said, the breakthrough occurred at least 2 weeks ahead of schedule on August 22nd, very successfully, and the TBM is penetrated through the bulkhead wall on the European transition box, and now it has been disassembled as we speak. Meanwhile, the interior structures are continue to advance in the construction. In general, in conclusion, is the owner as well as the contractor, they realized the high risk that project of this nature would entail. As a result of that, they establish risk mitigation measures early on to deal with the various conditions that were going to be encountered, such as complex and variable geological and hydrological condition, highly fractured rock, intrusion of dikes, mixed phase condition, high water pressure, high seismic conditions, and large tunnel diameter. They realized the importance of that, and they put the proper measures, including the having the independent design verifier to be part of the team early on and throughout the various phases of the construction. As a result of that, they selected a suitable TBM, and they implemented seismic joint at the interfaces, and they adopted a flexible NATM design with toolbox that to meet the various ground conditions. And the project has been completed successfully ahead of schedule. At this point, I would like to thank you all and open it to questions and answers. And if we run out of time, you can always reach out to me or to Vojtech at the emails shown here on this slide. Thank you.
Thank you, gentlemen, for that wonderful presentation. At this time, we'd like to invite all of our participants to use the chat panel to submit their questions. I'll read them off so they can be captured in the recording. Just as a note for our attendees, we are recording today's session, and the recording will be available within 48 hours on the UCA Young Members website. The first question, gentlemen, reads, what drove the decision for the upper deck to be cast in place and the lower deck to be precast concrete?
I think I'm going to take this, this question. We looked at the time to see whether we can provide a precast for the upper deck as well. There were several issues that would impact the ability to build a precast upper deck. One of them was, among them I should say, is the geometrical configuration. In order to be able to bring the panels and lift them and rotate them and put them in the right place, we were running out of room, which would require two-step process in which to place the segments, then go back and grout that space, the void that is between the two, and that grout would add additional operation. And the space that is required on the sides in order to accommodate the precast panel lifting and rotating and placing it is significant, and that's why the decision was made to go ahead with a cast in place. As to the lower deck is can be fabricated easier because it is narrower, obviously, and we have the room to be able to lift and rotate and set it up to the proper elevation and the proper cross grade.
Wonderful. Thank you so much. We have another question coming in. How is the potential smoke kept from one deck layer from the other? Were dampeners used between the two deck layers, or were there separate tunnel ventilation systems?
The two decks were not connected except at the emergency exits, and the emergency exit or the connection between the upper and the lower decks were pressurized. That those compartments were pressurized. So in a sense, if there is a smoke in one of the two decks, the other deck will remain smoke-free and will be utilized as an emergency escape. The fact that the two decks are having jet fans and the ventilation system toward at the end, the exhaust system at each end of the tunnel, as a result of, in case of a fire, one of the two decks that where the fire is will be operating in exhaust, while the deck that has no fire in it will be the fans will operate in supply to create a differential air pressure between the two, and this way we will keep the smoke in the deck of the incident.
Excellent, thank you. The next question reads, oh, we're starting to get a lot of questions all of a sudden. Let's see, the next question reads, what were the expected ground behavior types or failure types, and did you face any surprises during the excavation?
There were about 4 up to 5 ground behavior types in the trachea formation, and a combination between the RMR and the Höcken-Brown criteria were used to define the ground behavior itself, and also to design the shotcrete lining and also the rock bolt pattern for the various, or corresponding, I should say, ground support classes. There were generally no surprises as far as ground and support classification is concerned. In the beginning of the initial drive, where the shallow cover existed, the overburden behaved a little bit more on the deformation side. In other words, the deformations were larger than anticipated, but did not exceed the level 2 limits, and therefore additional support was installed, and as needed the excavation phase was made smaller to be able to better control the ground behavior.
Thank you. The next question reads, what was the single biggest advantage gained for the overall project by hiring the independent design checker?
I'm sorry, you will have to repeat the question for Nasri, because I was now in possession of the headset. Sorry.
Of course, no problem. The question reads, what was the single biggest advantage gained for the overall project by hiring the independent design checker?
What we believe is a major risk management is to have the independent design checker. This is design build, or a BOT, I should say it's a BOT project, in which the owner will get the project after 26 years of concession period. Therefore, it has to be, everything has to be self-certified, and in order to be doing self-certification, you would need to have a complete set of eyes, in a sense, looking at everything being designed and being constructed, and that was the role of the independent design verifier. There is a similar approach in the UK, which is called level 3 checker. However, for this particular project, all elements were required to have independent verification, independent analysis and review. So we look at it that is a fresh set of eyes, as well as a risk mitigation measure that the owner as well as the client decided to implement, which was very successful. Okay.
Wonderful. Thank you. Okay, the next question reads, what was the seismic joint made of, and how much movement could it accommodate?
The seismic joints consisted of 2 steel rings, as you can see actually in this picture here. This is one of the seismic joints. 2 steel rings and 2 hybrid rings that are partially steel and partially concrete. They have significant stiffeners to provide the rigidity that is required. However, the joint itself, to allow movement by having the omega seals that were provided, two of them on the back side. So in a sense, in a seismic event, the joints can open or close in the longitudinal direction, contraction or expansion by up to 75 millimeter, as well as can transversely move up to 50 millimeter. This is the amount of movement that is anticipated to be able to take from a seismic event at that location.
Thank you. Let's see, our last question reads, what constitutive models were used in the finite element models?
I will have Vojtech reply to that one.
Okay.
We decided after, again, discussion with the designer that in this case, and to describe the trachea formation accurately, we would use simply a Moore-Coulomb criterion where cohesion, friction angle were essentially derived from the Hoek and Brown criteria.
Excellent. Thank you, gentlemen. That seems to be our last question for today, so I'd like to give you gentlemen an opportunity if you'd like to make any final closing statements.
Thank you. It is very interesting, very challenging project. We would like everyone who has been involved in this discussion is to follow up on the project on the internet and through other references and other conferences and so on. One thing we would like is to take the opportunity to thank Yapi Merkezi and SK, the client who entrusted us in doing this, and to thank the designer, Parson Brinkerhoff, who we had excellent relationship working with them on this particular project, as well as their sub-consultants, in addition to all other parties who were involved in the project.
Thank you so much, gentlemen. Vojtech, would you like to make a closing statement as well?
I can only second what Nasri said, but it was a fantastic experience to work with this international team and really to bring international tunnel design and construction experience together in Istanbul, and it seems to be more and more the type how the experts and designers and contractors are being brought together on a very international basis, basically at any place in the world. So I think we are moving in the right direction. And again, thank you very much for the opportunity to speak to the audience today, and to you, Shen, and for organizing.
Thank you. On behalf of the UCA young members, I just wanted to thank Nasri and Vojtech again for their presentation today, and thank all of the attendees for participating. And definitely check out our website for details on next month's webinar when they're posted. And ladies and gentlemen, this was the end of our session for today. We'd like you to reach out to Nasri and Vojtech via the emails on the screen if you have any further questions about this project, or as Nasri had mentioned, checking on the internet for the project updates. And we'll be sending out an email to all attendees with a copy of this recording once it's posted on the UCA Young Members website. Thank you again for joining us, and we look forward to the next presentation of the UCA Young Members on October 28th. Have a great day, everyone.